So phase one was to collect data. This data would be used to prove the processes, prove the algorithms, and show the potential of the solid model engine. Two sets of data that were needed. The first being high resolution point cloud data of the bridges, and this was scanned, and I'll discuss that in a moment. And secondly, the high resolution photography that would be needed to apply and use within the defect detection process. So those two separate, distinct data collection processes is what I'll discuss here in the next few slides. The tools we can talk about next. Tools for the laser scanning, the point cloud collection, there were three different scanners that were used. Trimble, Faro, and Leica systems, all with various different rates of collection, processing speeds, laser collection, but essentially all producing point clouds where each point was a XYZ location of part of the bridge. And let's just for a moment discuss what that means and talk about how laser scanners work. So essentially what we have is a device that sits on a tripod, and that device rotates around and pivots in the vertical plane, and it shoots out a laser beam. That laser beam is then bounced off of the structure that you're measuring, and the time it takes for that beam to return to the device is measured, and that gives you a distance. This is done very rapidly so that laser points are shot out as it rotates in each plane and collects millions of points of data of the object. And this set of points is what we refer to as point cloud, and is the source for the processing for our solid engine testing and the processing afterwards. So really just a very complicated set of XYZ locations. Now, as it's not possible just to place this at one location and have the scanner collect the whole bridge, because there will be areas that are in shadow, or one side of the bridge won't be visible from certain locations. What to do is set up a protocol where points are chosen to place these scanners and to collect as much information as possible and without shadows. So the good example here is under the bridge. There were beams laterally across the bridge, and we needed to make sure that we collected the underside of the deck between those bridges. So had we only done one or two of these stations, we would have certainly seen some shadowing. So we had to collect a very accurate model. Now, once these collection stations have all been collected, then the processing then takes place, and we'll talk about that in a moment. So this is the protocols that we used. A laser scanner device placed under certain positions and moved around these bridges and so forth. Then for the collection of the second set of data, that being the photography, we essentially just used a very simple setup of a digital camera with a nice lens on it that allowed us, even though we were standing very close, to get very accurate, high density, high resolution photographs of the bridge structure itself. And you can see from this slide that these photographs gave us the ability to collect cracks, defects, and such that were relatively small, within the millimeter range, but that is what was needed for this accurate defect detection. The protocol in that case was to collect at a close range so that the camera and the picture itself would enable a resolution of 0.1 millimeter, and that's significant as it's a definition of cracks in many countries is at that level. So we needed to be able to collect them so the processing engine would be able to see them and detect them and identify them for us. And then secondly, the key thing here with this photogrammetric process, where these photographs are applied, that are applied to it, we needed a lot of overlap. To be able to see the same spot in a number of photographs allows us to then to determine distances and measure accurately. So there was a high level of overlap needed. So we couldn't just take one picture of the side of a column, we had to take multiple pictures. So these two processes, the laser range finding with the scanner and the photography, out at a number of locations around the globe, some in Atlanta, some in Cambridge in the UK, and some in Haifa, Israel. Again, this was to collect data for the front end to allow the engines to have something to work on and to test. So let's take a look at some of the what is possible. So we can see here's a bridge in North America, outside of Atlanta, and this was one of the bridges that was scanned at a very high level of accuracy. And you can see from the photograph in the lower right of the screen here, here are the beams I was discussing, and you can see the underlying part of the deck is very clear as we did scan between every beams. Very high level of intensity. Another example, again around Atlanta. Again, these 3D views that you're seeing are colored, in this case, just by some kind of variable. Here it's probably just height above the road. So each pixel is just given an independent color around that. Moving on to some examples from the UK. In this case, these 3D images were the 3D models, the point clouds, were draped, if you like, with the 3D images that some of these scanners can also take photographs. So you drape those photographs, and it gives you this very realistic looking 3D view. But essentially, again, it is just a point cloud that is an input to our processing. From Israel, we can see another point cloud that's colored according to simply here, I believe, height above the road. So those are some examples of what is possible. Those point clouds can be very dense, they can be less dense. It's entirely up to the protocol. In our case, we used a very high level of accuracy and density to ensure that the solid engines had enough information to be able to build the 3D model and extract the geometries of the beams, of the supports, and so forth. So that high level was necessary. On the photography side, the high resolution close-ups, you can see some of the examples here. Very clear photography was necessary. Again, some more examples here of a column, and you can start to pick out, we can start to pick out the defects visually. Obviously the goal here was to have the system, the process, to collect this data. Recommendations from this early phase. Obviously, first of all, the solid modeling processor does need large point clouds, very accurate, so that led to the need to have faster scanners, and then, as you saw, more survey points, more stations where the scanner is actually placed. And then obviously on the photography side, the more overlap you have, the better. So if that means taking more photographs or taking higher resolution photographs, that all benefits the engine and the processing that is put into. Obviously, both of those recommendations require very high levels of scanning. Really, in